All right, let's start off with a quick example. So when we're doing reverse chain rule, we're going backwards. And when we derive, remember we had to derive the inside and multiply it. Now we're going to derive it and divide it. If a function can be written in the form k f dash x, the derivative of f over f of x, you can integrate it using the reverse of the chain rule for differentiation. All right, let's have a look at an example where we have the integral of 2x over x squared plus 1. All right. Firstly, if I just take out the x squared plus 1 component from the bottom here, that can be rewritten as 1 over x squared plus 1. And we know that if we integrate that, or if we derive that, or if we make this the other way around, if we integrate it and we want to go back there, we know that the original function should be y equals log or ln x squared plus 1. Because if this is the case, then dy dx would create that 1 over x squared plus 1. However, we have to also multiply by the derivative of whatever's inside that we are logging, which would become 2x. And so we'd end up with 2x over x squared plus 1, which is exactly that thing. So if I say dy dx is given as this, and I say I is equal to ln x squared plus 1, where I is given as this integral, then we're done. So this would be the solution, because by integrating this, I'm actually creating that, which is going to get me that part there. Okay, let's look at a second example. Example number 2. I want to integrate trigonometric functions. Okay, this time let's say I is equal to the integral of cos x over 3 plus 2 sine x dot dx. All right, consider the following. So firstly, we're going to consider y equals ln the denominator, absolute value of it, just like we did for this. We just put it in the denominator, from the denominator into a log, and we derived it. So let's do the same thing. Okay, if we find dy dx, deriving that function with respect to x, we're going to end up with 1 over 3 plus 2 sine x multiplied by the derivative of the inside, derivative of that, which is going to be 0, and that's going to be cos x, or 2 cos x. Now, because this is 2 cos x, it's almost the same like this, except that we have an extra 2 there. So that means once we integrate it, we have to introduce half. So we say half of that would imply that once we've derived this and we end up with 2, that 2 will cancel out with that 2, leaving me with cos x over that, which is what I want. Okay. To integrate expressions in the form, so to integrate in expressions in the form k, the derivative of f over f of x, we try the ln or log of the denominator and differentiate to check and then adjust the constant. All right, so then adjust the constant after we derive. And if we look at these two examples, if we look carefully at these two examples, what we'll notice is that this derived becomes that. This derived becomes that. So we have an expression where we can extract f of x, and we can extract the derivative of f of x and the derivative of f. And so that is what we end up with. Let's look at another example. Okay, in this next example, we want to find out, given that I is the integral of 3 cos x times sine squared x dot dx. Looking at this function, all right, and if I let sine squared x obviously be the subject that I'm trying to find, if I differentiate by considering y equals sine cubed x and find dy dx, sine cubed x is the same as sine x all to the power of 3. So using the normal chain rule, this will be 3 sine x squared, which is the same as sine squared x, multiplied by the derivative of the inside, which is cos x, releasing cos x. But I had to know this. I had to realize to say, okay, well, maybe I should add 1 onto 2 to make it 3, so that if I derive it, it will go back. Because when I integrate any function, when I integrate a function and this function is like that, it ends up as the original. So if the original can be derived to get that, then that assumption will be made quite quickly and quite early, or considered, so to say. This is reverse chain rule, and that's 3 sine squared x times cos x. So under the consideration that y is equal to sine cubed x, we derive to get that, which is perfectly aligned to this. Therefore, the integral will be sine cubed x plus c. Okay. Next example. If I integrate x times x squared plus 5 to the power of 3 dot dx. Now, I'm not going to cube this function out. I'm not going to write it 3 times and expand the brackets and then expand x in. It'll take a long time. So what I do is, using the concept of adding 1 and considering the bracket, all right, I can say, I can use the word consider. Consider y equals x squared plus 5 to the power of 4. Therefore, dy dx will produce that, which will get me 4 x squared plus 5 to the power of 3 multiplied by the derivative of the inside, which is 2x. And when I just neaten this up, I end up with 8x x squared plus 5 cubed. So I have this 8, which I do not have over here. So therefore, if I let this equal to I and I want to find out the solution of this, then it would be 1 over 8. That would allow me, once I've integrated this, to cancel out. So introducing 1 over 8, all right, and y will be my solution, all right? So it will be 1 over 8 x squared plus 5 to the power of 4. To go back this way, remember, I have to derive. To go this way, I'm integrating. If I derive this function now, it would end up over there, but it'd be a 1 over 8 enough to cancel it out. Okay, so I've got to be smart about extracting that constant. So we've got this. We consider ln. all right? Or we consider the function as a power. In this case here, we're actually considering not len, we're considering the reverse of power rule by adding 1 to the power in the bracket and then adjusting the constant every single time anyway. All right. So if I have to write this out, to integrate an expression given as the integral of k multiplied by the derivative of f multiplied by f of x to the power of n dot dx, we try, or we just tried, using that same function, y equals f of x to the power of n plus 1, and then adjust constant from there. Okay, 2 more examples. If I have the integral of cosec squared x divided by 2 plus cot x all cubed. If I look carefully at this function, I can see that f of x is equal to the bottom part. And if I bring it to the top, basically, if I rewrite this as cosec squared times bracket 2 plus cot x to the negative 3, then like this, it would be in the form integral of k derivative of f times f of x to the power of n, where n is negative 3. Now, if I consider y equals to that to the power of n plus 1, so y equals to 2 plus cot x to the negative 2, and I then derive this, finding dy dx using chain rule, I'll end up with negative 2, 2 plus, and the derivative of cot x will come in afterwards. So minus 2 minus 1 is minus 3, taking me back to where I need to be, multiplying by the derivative of the inside, which is cosec squared x gets me the following. So therefore, after considering that, I know that I have to include this constant somewhere along the line. And if I rewrite this, it looks exactly like that, except I've got this negative 2, which is there. Oh yeah, this is supposed to be negative cosec, so that will be positive afterwards. So therefore, the integral of that, given that this is equal to I, will be given by y. It will be given by 2 plus cot x to the negative 2 and plus c, compensating or making sure that 2 times the required answer is divided by 2 so that it would cancel out eventually. And that would be my final answer there. Let's do one more of this. Okay. This time it's a definite integral, so from 0 to theta. And I'm given 5 tan x times sec to the power of 4x dot dx equals 15 over 4. And I'm told that theta is greater than 0 and less than pi over 2. We want to find theta, the exact value for theta, which is the upper limit of our integral. Okay, so I'm going to let I equals to this, and I'm going to consider y equals to sec to the power of 4x. Okay, if I do that, from there, I can see that the derivative dy dx is equal to 4 sec to the power of 3x multiplied by sec x times tan x, which ends up as 4 sec to the power of 4x times tan x. Okay, so these derivatives, remember, we have to know. Cot x derivative coming through there, and well, we know the other ones as well. So this is sec to the power of 4x. All right. Now that I have this in dy dx, I can then say the integral, is going to be equal to, firstly, dividing by 4, but we have 5 over there. All right. So at the same time, if I have to divide by 4, I'll write it like this: 5 over 4 sec to the power of 4x from 0 to theta. Then I would bring the 5 in and I would remove the 4 by multiplying by 5 over 4. The 5 will remain and the 4 will cancel with that 4. Okay, so I put 5 over 4 here to keep the 5 but cancel out the 4 once it goes backwards, or because it will go backwards. Okay. All right, so I got 5 over 4 sec to the power of 4. Now all I need to do is substitute this in here, and it will get me 5 over 4 sec to the power of 4 theta minus 5 over 4 sec to the power of 4 0. And this ends up as 15 over 4. And now from this, well, 15 over 4 obviously is what I need it to be. So I'm going to write this as an equation, make it equal to 15 over 4 on this side. And I end up with 5 over 4 sec to the power of 4 is going to equal like 1 over cos. This is like, remember, sec of 0 is the same as 1 over cos of 0. And what is the cos function? What is cos of 0? Cos of 0, it's positive 1. So this is going to be 1, which means this will be 1. So 1 to the power of 4 will be 1. So this whole thing will become 1, basically. So this will be 1, and then we add 5 over 4 on the left-hand side. It becomes 20 over 4 equals 5 over 4 sec 4 theta. From this here, we're now going to multiply by 4 on both sides, and we'll end up with, and divide by 5, and we'll end up with 4 equals sec to the power of 4 theta. Square rooting both sides, plus minus 2 equals sec squared theta. All right, square rooting both sides would end up with that. And then obviously I can then square root it again. And if I square root it again, then the negative ones will fall away. Positive one will remain. So negative is actually not applicable. I just need the positive. And I square root it again. So sec theta is going to be plus minus square root of 2. And so theta, once we solve this for that will become a very nice pi over 4. Okay, the only solution that is given in that range for this. Okay, the solutions for this is found by taking the reverse of sec, which is going to be 1 over cos. Theta equals 1 over root 2 plus minus, and that shoots out the solutions: negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4. And we know that in order to find these solutions solving for cos. Every time we have a cos graph and we draw a line through it, we always end up with two solutions. The first solution being theta, the second solution being 360 minus theta because of symmetry. Almost like a general solution. So with all of those solutions, we only have valid solutions that lie within this range. It will be that one there. So that's the only solution there for that.